Okay, guys. So we're going to be doing this video lesson. Is going to cover ionization energy and electronegativity, and then reactivity, and then summarizing everything together. So if you could get out your guided notes, and unfortunately, you're going to turn to a lot of blank pages. So I'm going to try and show you what was supposed to print up, and then you decide if you want to, if you can print it up at home, do it. If you want to try and jot this down where it's the blank pages, you could do that as well. So what was supposed to happen in your guided notes, and sometimes we send things to the printer, and if I don't say there's pictures, then it gets printed like before Chrome actually uploads it, and that's what happened this time. I'm sorry. But if you look on page 6, there was stuff that didn't come through, not as big of a deal. Page 7, this is what we're going to be talking about. This is the graphic organizer that normally should be up there. You know, you've got a whole page. If you could just make an outline of the periodic table, these questions are going to come up. But if you want to pause out and pull up, remember these are always available under the reference materials. You can go ahead and do that. Page, what was that? Yeah, this is page 8. It's the same idea, but electron negativity is in the center. If you want to pull that up, you can. We missed it for reactivity. Like, it's the same thing, but then reactivity. And then yours is just showing up blank, except I think like you see this summarizing the periodic table. There should just be an outline of the periodic table here too. So all of that missed. If you have the ability to print, you might want to print up pages 7, 8, and 9, and then tear out those empty pages and replace them with these. If you don't, you can just hand draw this in. It's not that big of a deal either. Okay, so we're going to start with looking at ionization energy. I got to get back to the right one. I was goofing around over here. Okay, so ionization energy. You learned in yesterday's lecture video lesson why atoms want to become ions, how it changes their electric configuration, and this kind of relates also with ionization. I'm trying to have my picture up here. I really don't like this, but I thought maybe you want to see the person behind the voice. So I decided to do it. Okay, so what is ionization energy? It is the energy that's going to be required to remove an electron from an atom. So we're going to see a trend on the periodic table of what happens as the electric configuration changes for an atom. How much energy would it take to actually pull an electron from that atom? This is a graphic. They can be difficult to interpret, so kind of catch what's going on. We used it before with atomic radius, so atomic number is down here. So if I kind of look at this guy, I'm in the second period here. So this would be atomic number 3, 4, 5, 6, 7, 8, 9, 10. So I'm going, if I go look at this line right here, I'm going left to right across the periodic table. So what happens to ionization energy as I move left to right? It would increase. If I look at this top part right here, this would be going down the same column. Okay, so down a group. So as I go down a group, no matter what that might be, the ionization energy decreases. Okay, so let's try and sum that up, and then we're going to talk the why behind it. So as we go left to right, it increases. Well, why is that? Remember, ionization energy is the amount of energy it takes to rip electrons from that nucleus. So atoms on the far right of the periodic table do not want to give up electrons because they're getting closer and closer to the octet rule, right? So it takes more energy to rip them from the atom. As we're getting closer to the octet rule being filled, getting to nitrogen, oxygen, fluorine, all those halogens, they don't want to lose electrons. So it's going to take more energy to get rid of them, where things like lithium, they don't want that outer electron anyway. They want to get rid of it. This is stuff that you looked at in yesterday's video. So they say, hey, take it. I don't want it anyway. It's kind of like whenever your mom gives you carrots for dinner, and then all of a sudden, I don't know, your sister who is a vegetarian or something will eat all your carrots and you didn't want them anyway. So you're just like, hey, take it. I don't want it. That might have been a horrible example, but it was the only thing I could think of. Okay, so ionization energy, what's going to happen as we go down a periodic table? So as I go down a group, so down the alkalis, alkaline earths, halogens, noble gases, what's going to happen? It's going to decrease. Okay, why does it decrease? Electrons at the bottom, so those are further from I really probably should. The electrons at the bottom of the group. So when we look at the atoms like cesium, francium, so the ones at the bottom of the periodic table, those electrons are further from the nucleus, so it's easier to remove them. So the nucleus that's help holding those electrons in by electrostatic attraction, right? Positive, negative. There's more of a distance, atomic radius is bigger down there, and so it's easier to rip. And it's always the electrons that are furthest away from the nucleus that get ripped, get pulled away from an atom. And it's easier to pull those away because they're further away from the nucleus because we have more energy levels, right? So if we were to do this and we draw it a little different with the trend, you're going to see why. It's this whole concept of the head of one arrow is going to hit the tail of the other, because you're going to have to memorize the trends. It seems intimidating right now, but whenever we put it all together, I try to come up with a way that makes it a little bit simpler for you to catch all the trends. So even though we just wrote the opposite, that it decreases as you go down, well, flip it around. It increases then as you go up. And you're going to see why I do it like this. Okay, so that's ionization energy. Electronegativity is something that we're going to use a whole lot of. Ionization energy is an irritating number to deal with, so we flip it into this concept called electronegativity, and we're going to use that whenever we start to learn about bond polarity, whether it's within a bond or whether it's in a compound. So polarity makes a huge difference with how a certain chemical might react or not. So what is electronegativity? It's the atom's ability to pull more electrons to itself. So think about right now, before we even look at the table, when you look at a periodic table, boom, so like over here, don't even know if you can see it, but whenever you look at this periodic table, here, let me make this bigger if I can. Think about which elements on this periodic table, trying to stay focused, are going to want more electrons. Like they're just so close for that octet rule to be filled that they want more electrons, okay? And wrap your brain around that along with electronegativity. So be thinking as you look at that periodic table, which ones want more electrons? I'm sure that you love the little game we're playing. Okay, so again, what is it? Atom's ability to pull more electrons to itself. Some of these groupings want electrons a lot more than others. Okay, so let's make sense of this again. If I look at this line, this is going left to right. So as I move across left to right on the periodic table, those atoms, as I move to the right, they want more electrons. Their electron negativity. It's like I like those electrons. Their electron negativity increases. As I move down a group, electron negativity decreases. Okay, so as we look from one line to the next. So let's summarize this. Left to right increases. Why? They're so close to octet rule being satisfied, right? Atoms on the far right of the periodic table want more electrons to have a complete octet. They're very, very close already for it being to that complete octet. So electronegativity is how much it wants more electrons. And what happens as you go down? It decreases. Why? Okay, atomic radius increases, making the ability of that nucleus, that positive nucleus, to attract more electrons harder. So as we go down, atomic radius increases. Why? Because energy levels increase. So therefore, that positive tiny little nucleus has a harder time attracting more electrons into its core. Okay, makes it harder, so it would decrease. Summarize it on a periodic table. Let's put it like this. And again, you're going to see why we are writing it like this with the arrows for the periodic table. Okay, you guys, I know you're going to hit pause whenever you need to catch up. Okay, so reactivity. Next time I see you, well, depending on what group I see, we're going to be doing a demo with reactivity, so you can see it's pretty fun. At least I think it is. We get to catch metal on fire. So when is it not fun to actually catch metal on fire? So we're going to look at alkali metals and see what happens. So what does it mean? Just how readily an element wants to react with any other element, okay? Or compound, I should really say. Just how readily an element wants to react, okay? Reactions happen because of electrons. Electrons are the driving force of reactions to happen. Octet rule is a driving force for electrons to even want to move around for a reaction to happen. Reactions do not happen because of the nucleus not being happy. If that's occurring, that's nuclear radiation. That's a nuclear reaction. That's not what we're dealing with. Every reaction we ever watch is because electrons are wanting to dance around and change partners, okay? So what is and the reactivity trend is really different. We don't get to look completely at just overall in the periodic table. We have to look at metals and separate their trend from nonmetals. So the most reactive nonmetal is fluorine. It's so reactive that as of late, there's only 2 labs in the world that will even house pure fluorine because it is so reactive. Why is it so reactive? Really just a combination of all the trends. So the atomic radius has a smaller atomic radius. It has the most electron negativity. The ionization energy to rip away electrons is huge. So all of those things make it extremely reactive. What's the most reactive metal? Francium. So francium likes flow, fluorine. Francium likes flow. So why is that? Same thing, just combining all of the trends on the periodic table. So atomic radius, electron negativity, and then ionization energy. We can put this, but we draw it a little bit different as a trend. We actually kind of slice right through the periodic table. So if I look at my nonmetals, which remember nonmetals really are only over in this area right here, but as we go up towards fluorine, they're going to be the most reactive. We totally ignore the noble gases. Think about why. They don't react. They're inert. They're happy, right? Octet rule is complete. So if I say what's the most reactive nonmetal, or I say true or false, helium is the most reactive nonmetal, you better say false. It's happy. The noble gases are out of the equation. Most reactive metal, francium. And so then the trend kind of goes in the opposite with that one, okay? So then we could summarize all of this into one big periodic table, and that's where you're kind of at the bottom. You know, maybe you did decide to print this out, but if we summarize everything, I'm just going to put all of this up here, let you guys take a look at it, and then I'll talk about it. I had to find my agua. Okay, so I had a student once, and this is why we do the head to tail this way, because you do have to memorize this, and you're going to have to compare one element to the next. But let me get my irritating face way over here. So, you know, it's always tricks in how you memorize these things. And this student said, hey, well, let's think like this. Like energy is kind of like heat, which heat is a form of energy, and heat always rises. So ionization energy, just think heat rises, and the arrow went up, and then you always connect the head of one arrow to the tail of the next. So it's kind of easy once you realize that it goes like that. And just ionization energy, the 2 letters, those go on the same one. So electron negativity, ionization energy, you know, think heat rises. It's going to increase as I go up and to the right. And then the radius is just the opposite. Okay, so radius is going to increase as we go to the left, and then the head of this connects to the tail of the next, and as we go down. Then, like I said, if you remember, francium likes flow, most reactive metal, most reactive nonmetal, then you can compare a trend. So in other words, if I say, okay, whatever this, did not mean to do that. So imagine whatever element that's right here, which is what? Iodine. Which one's the most reactive, iodine or fluorine? Well, if this dude's the most reactive, then obviously fluorine. If I say what's most reactive, iodine is right here and chlorine is just above it, chlorine's more reactive because as I go up, it's more reactive. If I go over this way and say what's the most reactive, let's see, sodium is in this box, right? So sodium that's here, or potassium, lithium was in this box, sorry. Lithium that's here, or I'm trying to do this, potassium that's down here, you would be able to tell me that potassium is more reactive. So that's what you're about to get practice on, and we're going to do a lot of this in class. Remember, we're flipping the classroom a bit. At home, you take notes, and then in the classroom, we do some demos, and then we do some practice together so that we're ready, available to help you out. But come up with a way to memorize these trends. We're not going to give these trends to you. You have to just remember them, fill it in, know how to apply it. Okay, so that pretty much summarizes what you got to do for notes for today. If you have questions next time you're in class, make sure and ask. And otherwise, we will see you soon. Maybe. I just have to know how to stop this. Oh, there.